Good evening, everyone. Welcome to the week 3 live interaction session for the course Mechanical Operations. So, as usual, let's just wait for a few minutes for others to join before we begin our session for today. So, I think we can start our session. Let me just share my screen. I hope the screen is visible and I'm audible. Okay. So, welcome to the week 3 live interaction session for the course Mechanical Operations. This course is offered by Professor Shabina Khanam ma'am from the Department of Chemical Engineering IIT Roorkee under the NPTEL SWAYAM program. Myself Pratyumnan, a PhD research scholar from the Department of Chemical Engineering IIT Guwahati. I am responsible for conducting the live interaction session for the course for this particular course in the July-November 2026 semester. So we have come, so 50 percentage of the course is almost done, and today we enter into the week 3 session. So in the first two live interaction sessions, or in the first 2 weeks of course content, we basically focused, or our main emphasis was on understanding the mechanical operations, how basically what is mechanical operations and how to deal with the different sizes of particles. We basically dealt that with the respect to the particulate and powder technology. So we did see about the different kinds of sizes and shapes of particles uh, that the feed will have. So we did discuss about the fact that the material that we are going to handle the in real life is not going to be uniform in shape, or it's not going to be a regular polygon. It's going to be an irregular shape of material. So we did discuss about the different kinds of features relevant to the shape and sizes of the material. Once after that discussion was completed, we went on towards looking for how to separate these particles based on their sizes. So if you remember, based on that, we did the measurement of sizes of the particles, and based on that we were able to do this particle size analysis. And then after that, we discussed about different types of screen, the industrial screening equipments that were used. I hope we are able to recollect what was discussed related to the industrial screening equipment. The different types of screens that were used depending upon the type of feed, the size of the particles that were present in the feed. Then we did talk about or solve problems related to related to the calculation on the effectiveness of the screen, their aperture size, and then the two different kinds of models that were relevant for fine particle analysis. So if you remember that fine particles are very small in size, so general models will not be useful. So we went towards discussing about two specific models. One is this Rosen-Ramler model and another one is GGS, Gates. I hope you are able to remember Gates-Gorman-Schumann model. So we did say that Rosen-Ramler method is actually going to be mathematically more complex. So we limited our scope of discussion to the GGS model. So this was what we, and then at the end we did discuss about comminution as a process in mechanical operations. So there we just discussed on what is this comminution processes. So it's nothing but it's basically this reduction. How do you do this size reduction of the particles? How do you break the particles into a smaller size? So that is the comminution process. So today in week 3, we will mainly focus on the laws that is related to comminution and the size reduction equipments. So I hope, sorry. So in this law, so basically for the size reduction to happen, we need to apply some amount of energy. So based on the amount of energy that we use, that actually forms the basis for the laws of comminution. So that is something that you need to remember or keep in mind. If it is asked like what is the basis for this laws of comminution, or how does these laws are framed for this process of comminution, they are framed on the basis of the energy that is consumed during the size reduction. So that is the basic um, basis for the formation of these laws. So let me write it down. Their basis is energy that gets consumed for the creation of new surfaces. Sorry. Yeah. So when you are going to break a bigger chunk of material into smaller pieces, you are basically going to generate new surfaces. So how much amount of the energy that will be spent in the uh, in this process is what forms the basis for the framing of these laws. So there are typically three types. There are typically three laws. So one is the Hicks law. Another one is the Rittinger's law. And after the Rittinger's law, you have something called as Bond's law. So all these three laws are basically framed on certain assumptions, and of course they do have certain limitations. So we will discuss each of them one by one. So in case of Hicks law is usually expressed, or you can say It is nothing but the required to work required for crushing, just a second, for crushing a given quantity of material is constant for a given reduction ratio irrespective of their size. So the amount of work that you need to supply, so energy as such you will supply to that material in the form of some work that you are going to do on the material. So the work that you put on the material in order to crush the material into smaller pieces, that particular work remains constant for a given reduction ratio, and that is going to be irrespective of the size. So what it typically means is the amount of energy, let's say E1 amount of energy you say is actually required for breaking down a particle which is approximately 300 mm in diameter to 100 mm in diameter. So let's say this is the E1 energy that is required to break a particle which is initially of 300 mm in diameter to particles which are 100 mm in diameter. Now again you have another process, you can say, wherein you are going to break a particle which is 30 mm in diameter to 10 mm in diameter. So what this says is the reduction ratio. So reduction ratio is defined as diameter of the particles in field to diameter of the particles in the product. So if you see in both the cases of E1 and E2, or you can say process 1, and this you keep it as process 2. In both this process, the reduction ratio is 3, right? 300 by 100 is 3, and similarly 30 by 10 is also is going to be 3, right? So irrespective of the size in which you are actually breaking down the particles to, since the reduction ratio is going to be constant, the work that is required will also remain same. What it typically means is E1 should be equal to E2. And where was I? Yes. So E1 should be equal, E1 becomes equal to E2 in this case. So when this happens, so in case of Kick's law, this is true that work, so the E1 and E2 is nothing but it's going to be the work that you are going to do. That is going to remain constant for a given reduction ratio irrespective of the particle size. That is what exactly uh, is represented here. So since the reduction ratio is going to be 3 in both the cases of process 1 and process 2, the work that is required will also going to remain same. So how do you express this work? So work is represented as energy that is required to crush a quantity of the material divided by m, that is the amount of material that you are actually going to break down, should be equal to k, let me write this, k ln df df by dp, which is nothing but the diameter of the feed and diameter of the product. df is diameter of the feed and dp is going to be the diameter of the product. So the work is nothing but it's basically the amount of energy that is required for crushing a given mass of material, which is nothing but is equal to kk, that is your Kick's law constant, or you can say Kick's constant. This is nothing but it is Kick's constant, and df by dp is going to be a reduction ratio. So in this case, if you see W1 and W2 or E1 and E2 for the given quantity of the material is going to remain the same. But that is actually is what is also the limitation of the Kick's law. The major limitation for the Kick's law is that they say that if you are going to keep the reduction ratio constant irrespective of what kind of size of particle is involved in the process, the amount of work that you require to do in order to crush the given quantity of the material is going to be constant. However, in real conditions, this condition will not be satisfied, or this condition will not be applicable, because when you go for breaking particles from, or when you're going to break a bigger size particle, let's say 300 mm to 100 mm, that amount of energy that is required is going to be less in comparison to breaking a 30 mm particle to a 10 mm particle, because there the amount of energy that is involved in the process is going to be actually very high. So the energy that is actually required to break the particles into finer grains is going to be more expensive. I mean, it's going to be more energy expensive compared to breaking a particle which is actually bigger in size. So that is one of the limitations. Amount of energy required to break particles to finer sizes is more compared to porous particles. So this is going to be one of the major drawback or the limitations of the Kick's law. The Kick's law assumes that the amount of work that you are going to put in to crush a material is going to be constant for a given reduction ratio irrespective of the size of particle. However, in the real conditions, this becomes a limitation, because the amount of energy, or you can say because breaking a particle into finer grain size is going to be more expensive energetically, or you can say is going to be energy expensive compared to the amount of energy that is required to break the particles into more porous size. So you can actually say that this particular Kick's law is applicable only for porous grain particles or porous size particles. So this is their limitation. Now, since there is a limitation, there are other laws that are proposed to overcome this. So that's how the Rittinger's law was developed. In Rittinger's law, what it actually states that the work that you are going to use, or work that you are going to put for this reduction, is directly going to be proportional to the new surface that that is getting created in the process. So I hope no questions in between. In case if you have any questions, you're welcome to let me know. Any questions? Okay. So Rittinger's law as such, what it actually says is, so first I'll give it as a statement, then I'll write out the formula. So the work that is required for size reduction is directly proportional to the new surface being created in the process. So basically the comminution or the size reduction process is a process wherein new surface is actually going to be generated, right? So that is how the Rittinger's law also uh, is related. So there they try to relate the amount of work that is done for the size reduction to the new surface that is actually going to be created. So if you want to write that, then work that is done or the work that is spent on the size reduction process is nothing but it's equal to E by M, that is the energy that is required for crushing a given mass of material, which is nothing but it's equal to K R times SP minus SF. Oh, okay. So KR is nothing but it's going to be same like Kick's constant. This is going to be like this is going to be called as Rittinger's constant, and your SP is nothing but it is the specific surface of the product, and SF I'll just write, sorry, and SF is nothing but it is the specific surface of the field that you're charging inside the size reduction equipment. So now, since it is talking about the specific surface of the product and the feed, and we don't know the values, we try to express SP and SF in terms of the known parameters. So what is actually known to us is the diameter of the product as well as that of the feed. So if we are able to express the specific surface of the feed and the specific surface of the product in terms of its diameter, then our work will be much more simpler. So for this, what we are going to do is we are going to express this SP and SF in terms of the Satchel diameter, which is nothing but dv dvs. I hope you are able to remember what does this diameter actually represents for. dvs. In the first live interaction session or the first week of course content, this was discussed. So anyone who remembers this, what is dvs? Anyone? Yes, no. So DVS, please, in case if you are not able to recollect, kindly have a look at the course content or probably the live interaction session slides if you have, or if you, whenever you find time. So DVS is nothing but it is the diameter of the sphere equivalent to the volume to the surface area of the particle. So now we are going to express SP and SF in terms of dVs. So if we express that, then the equation will be converted to this form: 6 kr by rho 1 by dvs of p minus 1 by dvs of f. So this is how you write the equation. So Kr is the Rittinger's constant, rho is going to be the density of the material that you are going to actually crush. dVs is the Satchel diameter of the product, and dVs of F is the Satchel diameter of the feed. So this 6 Kr by rho can be expressed as, can be simplified as Kr dash times times 1 by dVs of P minus 1 by dVs of F. So this is the work that will be required for the size reduction as per the Rittinger's law. Again, as I said, there again is a limitation. So just like how you saw that Kick's law is applicable for particles, for porous size particles, in case of the Rittinger's law also it has a limitations. So the limitation is this is largely largely for fine size particles. So this is one of the limitations. So this is basically useful for fine size of particles. Where the, so as the particles becomes finer in size, the amount of surface that is going to be created is going to be actually more. So that is one of the major limitations. Just like how you saw in case of the Kick's law, it's only applicable, or it only is it's typically applicable only for porous particles. Similarly, Rittinger's law is going to be applicable only for fine size particles. And apart from these two limitations that is specific for each of these two laws also share some of the limitations in common. So that also I'll state it here. Kick's law and Rittinger's law limitations. First thing is, the sizes of the particles that you can treat is limited, as I explained above, is limited, as I explained just before. And second thing is, the amount of energy that is involved the amount of energy that is used in the process does not account for the mechanical losses of energy that happens during for the mechanical losses due to friction and inertia. So in any kind of equipments that you use, whatever the amount of energy that is going to be spent is not like it is an ideal case where there is no other wastage of energy. Whatever the entire amount of energy that you're going to spend is actually used for the entire purpose or is used for the intended purpose. In between these two, you also have the losses that usually happens during this process. So when the size reduction process is going to happen or is happening, that equipment what you are going to use for this size reduction process, through them as well some amount of the energy is actually going to be wasted. So that friction and the inertia, because of that also some amount of the energy is going to be wasted for that, and that particular mechanical losses or that energy losses is not being accounted for in both these Hicks law and Rettinger's law. Both these laws assume that there is no energy loss or there is no mechanical loss of energy because mechanical loss of energy in the size reduction process. With that assumption, these laws have been proposed, but in real life conditions that is not the possible. It's not just typical only to size reduction process, but to all sorts of engineering, or you can say machinery. In case of every process, if you see, whatever the you cannot always get 100% conversion or 100% utilization of what you actually intended. Some amount of the material or energy is actually going to get wasted in this process. So similarly, in any case of engineering applications also, if you see in any industrial applications also, whatever the amount of energy that you're going to supply in, it is never possible that all the energy gets used for its intended application. Some amount of the energy actually gets wasted in the form of heat or uh, some other sources of energy, or in some other form this energy will be actually wasted. So that particular amount of energy also needs to be accounted for, because the major reason why we have to account for those energy is so that we can actually know how energy efficient the process is. In case if the process is not going to be energy efficient, then that process is not going to be profitable in a practical setup. So as such amount of energy that is used in the process is actually, if you check, if you see, it's actually going to basically relate to the amount of money that you invest into the system. So if your process is not going to be energy efficient, if let's say 50 to 60% of the energy is going to get wasted, then probably that will not be a very economical setup. So you need to change the process. So you need to actually account for those energy losses so that you can do design improvements within the system, so that you can minimize these energy losses and improve the energy efficiency, which at the end helps in improving the profitability of the process that you actually do. So in order to this particular aspect of knowing how much amount of energy is going to get lost in a system is actually very important, not just for size reduction process but for any industrial or any engineering applications that that you're going to tackle. So this particular Kick's law and Rettinger's law have have these two limitations. One is the size of the particle. It can only treat only limited size of particle, and second is it does not account for the mechanical losses of energy that usually happens during the comminution process. Now to account for these, there comes the third law, which is the Bond's law. Bond's law is usually Bond's law as such, if you see, it basically is applicable for various sizes of particles, various sizes of free particles, and it also accounts for the loss of energy that usually happens during the size reduction process. So, quickly speaking about Bond's law. So, Bond's law, the statement goes somewhat like this: the work required to form particles of size dp from a very large particle is proportional to the square root of sp by vp of the product. So if you're going to express this mathematically, what you're going to end up is work that is required for crushing the particles is equal to the amount of energy that is used up in the process to that for crushing m quantity of material, which is nothing but it's equal to k times sp by vp whole power zero point 0.5 or square root. That's what it means. So SP by VP can be written as 6 by dP. I hope you know how we write SP by VP equals to 6 by dP. So quickly showing the you can say, what you can say. Quickly showing how to calculate. So SP is for a spherical particle is nothing but it is pi dP square pi dP square, and Vp is going to be pi dp cube by 6. So if you divide sp by vp, it's going to be 6 by dp. So now if you rewrite this expression, it's going to be work done is going to be energy by mass times k by 6 times dp whole power 0.5. Now you remove the 6 out of the square root. So work done is equal to energy by mass, that is kb times 1 by dp whole power 0.5. So which where kb is nothing but Bond's constant. So if you're going to use if you're going to introduce so more precisely, you can write this as a again I will write this expressions will be formatted when I am going to upload the presentation. So here this is just to minimize the workload so that we don't lose up on time. So this is how you write that for the Bond's law, and the kb is the Bond's constant, and this Bond's constant is going to depend upon the type of machine that you're going to use, like like After this, we will discuss about the different kind of size reduction equipment. So this KB value will vary depending upon the type of equipment that you use, and then the material that is going to be crushed. So now we have something called as WI, which is nothing but the work index. So work index is nothing but, so here this is about the work that is actually required for crushing the material. Based on this, we actually define a term which is called as the work index. So the work index is nothing but it is the gross or the total energy. So this is something that is going to be specific for only for Bond's law, and this is not there. I mean, this is not something that is not defined in case of the Kick's law or the Rittinger's law. So Bond's law is nothing but the gross or the total energy required to for the you can say required to reduce a large feed of material such that 80% of the product will pass through 100 micrometer screen. So what it typically means is, so you take a 100 micrometer screen, and 80% of the product has actually is supposed to pass through this 100 micrometer scale. Now, what amount of energy do I need to supply in such a way that I can break this large particle into smaller ones, so that those smaller ones can actually go into 100 micro, so that those smaller ones, 80% of them at least, can actually pass through this 100 micrometer screen. So, the definition is more straightforward. However, here you need to note down that the energy that you are going to use is not going to be the is going to be actually the gross, the total amount of energy. Here you are going to actually include the mechanical losses also into the system. So that is how you define work index, and the expression for the work index goes as 0.3162 sorry, KB, as the relationship goes as 0.3162 times WI. So I hope it is clear. And again, for the feed size, unlike in case of both of those coarse particles and fine particles, limitations that you observed in Kick's law and Rittinger's law, in case of the Bond's law, that particular size fraction or the size of the feed that you can actually treat is going to be a bit more larger. That range is going to be more. It is going to be between 0.05 to 50 mm. So typically speaking, the intermediate class. So Kick's law. So you can actually remember this thing. Remember it like this. Kick's law is for coarse particles. Rittinger's law is going to be for fine particles. Bond's law is going to be for intermediate sizes of particles. So the Bond's law is the one that is going to actually include or consider the mechanical losses of the energy that happens during the process. Any questions related to these three laws of commutation? Because after this we will move to size reduction. Over there we will see a very brief overview, and then we can progress towards the problems that we have for today's session. Any questions? Sorry. Any questions, anyone? Second, it's getting recorded. Any questions? Or shall we move towards size reduction stuff? Yes. No questions. Now I have a question. So in case if you see, in case of this Rettinger's law, we express this SP as 6 by rho dBSP. So anyone who knows how to express this in terms of this, why did I express it as 6 by rho times 1 by dBSP? It should be 6 by dP, right? I mean, it should be 6V by dP. As per this way of expression, I can write this as SP as 6 dP by dP. But why did I write 6 by rho times dBsp? Again, here it is dP, that is diameter of the particle. There it is dBs, which is nothing but the equivalent spherical diameter, and that equivalent relationship is going to be between the surface area to the volume ratio. But how did I express SP as 6 by rho dBsp? Anyone? Okay. Kindly let me know this. Think about this. How did I express? Because you need to know, I mean, when we go for mathematical expression, we need to have an understanding on how we are writing or how we are expressing one particular term in terms of the other parameters. So remember this and let me know how to express probably by this end of the session. Now come to size reduction equipment. So obviously when we talk about law of communication or communication as a process, we need to actually talk about how to reduce the size of the particles also, right? So for that you're going to require an equipment so that you can feed in or charge in the material. It breaks by whatever means it is designed to, and then it can give you the feel. But again, for different kinds of particles that you require, you actually need to choose a different types of a different type of crusher or a size reduction equipment, and also you need to have an understanding of the basic principle of mechanism behind this basic working principle behind these equipments, so that you can have an understanding of what particle size you can actually expect for, or what can be the shape that you can actually expect for. So in these particular cases, as engineers, it basically becomes important for us not just to know how to basically do the particle size distribution analysis of the products that we obtain by this crushing or the size reduction equipment, but also the working principle behind them, so that we can so that we can judge if I'm going to basically need a material of this particular size, what kind of equipment I need to choose, and what should be their working principle, or how they will be able to produce that material. As engineers, we are supposed to know this particular information so that we can get the right set of particles for any kind of application that you are targeting for. Because the major reason why we need to, I mean, the typical reason being is that you cannot do a hit and trial method, because each and every process is going to involve some sort of material that as feed, and then the equipment is going to run, so it's going to be a cost So it's going to actually affect the cost of the material or cost of the processing. So hit and trial method cannot be applied in this case because cost is involved, money is involved. So we need to basically have an understanding on this so that we can get the right set of particles for our intended application without much effort and money. So in this size reduction equipment, you will basically deal with the different types of mechanism for the for the type of reduction. So one is, as you can see from the table, we have compression, impact, attrition, shear, and then you have also some sort of non-mechanical introduction of energy. So we just need to know what does each of these terms mean. What is meant by compression, what is meant by impact, what is meant by attrition, and what is meant by shear. The last thing that I discussed, that is the the introduction of non-mechanical energy, that is more what you can say, non-conventional. It's something that is actually booming up or coming up in the industries, like using some sort of thermal shocks or ultrasound to break the particles. However, the basic four are these: compression, impact, attrition, and shear. So in case of compression, what you do is you basically split the particles or break the particles using a single force. In case of impact, the same breaking of the particles is actually going to happen by two rigid forces. In case of attrition, the particles are going to be scraping between two surfaces. In case of shear, it is going to be a fluid or particle-particle interactions that is actually going to break the material. So you just need to understand this. What is compression, or compression versus impact versus attrition versus shear? How they are different from each other? Their intended mechanism is same, to break the particles into smaller sizes, but then the way they do it in order to obtain smaller particles is going to be different. In case of compression, you use a single force. In case of impact, you basically hold the particle between two rigid forces. In case of attrition, you're going to scrape the particles between two rigid surfaces, and in case of shear, you are going to use actually particle-particle interaction or some sort of fluid so that you can apply shear force on them, and because of this shear force, the particle is actually going to break. Again, between in each different class, you have multiple types of crusher and grinder. So some of the example is jaw crusher, gyratory crusher, cone, crushing rolls, and you have roller mill, granular, hammer mill, attrition mill, tumbling mill, fluid energy mill, and so on. And if you go through the course content, you can find about each one of them in detail. As far as the this session is concerned, we will talk only about ball mill, because ball mill is something that is very important to discuss. I hope have any of you ever seen a ball mill? Any chemical engineers out there who have done this? Um, who works in such kind of places, or who has done this mechanical operations lab during your bachelor's, or currently you're doing it? Anyone? In mechanical operations lab, you can actually see this ball mill. So, has anyone ever observed or happened to see a ball mill? Anyone? Okay, so if you did not happen to see one, then probably in case if you are pursuing engineering, then if you in any kind of mechanical operations lab, you can see. So it's nothing but it's a rotating cylinder which is actually charged with the grinding media and then the feed that you're going to inject into them. So has a rotating cylinder and then the grinding media. So the grinding media is nothing but the steel balls or some or kind of balls that are actually made up of different kinds of material, and then your feed. So when it actually rotates, the feed material is actually going to be subjected to both shear as well as impact forces. So at lower forces or low speed, so this ball mill is actually going to rotate. So this cylinder is actually a rotating cylinder. You have a rotating cylinder, you have a grinding media, and then you feed into the material, and then you are going to actually rotate. Now, based on the action of the grinding media over the particle, the the particles split into different sizes. So, based on the speed of rotation, there are totally two types of forces which are responsible for breaking the particles. One is the nothing but is your impact, and another one is the shear force. So, when you are rotating the cylinder up to a particular speed, so you basically start rotating until it basically reaches a particular speed, it is the shear force which is actually predominant. Once you move or once you increase your speed above that threshold, it is basically the impact forces start acting onto the particles. So there are two forces that are going to be involved, and based on the speed of rotation of your cylinder, then different types of forces will act on this particle so that your a new particle is actually broken down. So this particular speed, or you can say the threshold speed, is called as a critical speed of revolution. So below the critical speed of revolution or critical revolution speed, you can say, it is going to be your shear force. Above the critical revolution speed or critical speed of revolution, it is going to be your impact forces, which is responsible for breaking down this particles. So if you want actually a finer size of particles, then you need to actually put more number of balls, or you can say high ball density. I mean the grinding media that you are going to use, the steel balls, they need to be highly dense, or you need to provide a longer residence time, or you need to use more finer balls. So there are different types of factors that usually affect the kind of material or the product that you obtain from a ball mill, starting from the density of the balls, the weight of the balls, the residence time, the speed of revolution, the kind of particles that you are going to inject, the type of the balls, I mean the material with which this grinding media is made. So it's not just only steel balls. Apart from that, there are also the ceramic based and antimony based grinding media are also charged into this rotating cylinder. So based on all these factors, the particles or the product that you're going to obtain is basically what is actually going to be influenced. So till now, any questions? So I'm going to stop the discussion here for some time, because again we are going to, I mean in case of size reduction equipment, each and every different equipment is discussed in detail in the course. So you are welcome to go through the course lecture for a detailed understanding. Here we have time limitations, and our main focus is to solve problems. So we will restrict our discussion for the timing till here. In case if you have any doubt, you're welcome to let me know now. Or let's take a short break for 5 minutes, not beyond that. And then we will resume our session from there. In case if you have any doubts, please let me know. Or for those who do not have any doubts, you can either take a short break or you can start solving the problems one by one. Anything is fine for me. So I'll be here. You can ask. Any questions from anyone? Okay. So if you don't have any questions, the screen will be shared. So try to solve the problems, or you can say get the answers for the question. Yeah. So I think we can start our, I mean, resume our session. Yeah, my screen is anyway, it is shared. So anyone with answers to any of these three questions that was displayed? Question one, two, and three. Anyone? Any answers? Okay, I'll read out the question. Which of the following statement is true for Bond's law? A. 80% of the feed should pass through the screen. B. 80% of the product should pass through the screen. C. 80% of the feed and the product should pass through the screen. And D. None of the above. Any answers? Yes, no. So the answer is 80 percentage of the feed and the product should pass through the screen. That's how it is defined, right? So the work index, if when we discuss the definition, we did discuss that both the feed as well as the product, the 80 percentage of that should actually pass through the screen. Any questions in this? The next one is much more simpler, but any questions in the first one? Any confusions? Anyone? Okay, next move to next question. This is a simple one. Mechanical loss of the crusher is counted in Kick's law, Rittinger's law, Bond's law, both Kick's and Rittinger's law. Yes, Bond's law, right? So that's how, yes, that's correct. So that is what actually we saw in the, limitation section. I mean, for kicks and retingers, they are not actually accounting the mechanical losses of energy that usually happens, whereas the Bond's law accounts for these mechanical losses. So, as somebody rightly said, the answer is Bond's law. Now, next question. Grinding medium is not used for which of the following mills? Black jaw crusher, hammer mill, ball mill, and fluid energy mill. Grinding medium. Again, this thing we discussed in terms of ball mill. So there we said that the steel balls are used as a grinding medium. So likewise, for other mills and crushers are also there where grinding medium is not required. So which of the following equipments does not require a grinding medium? That is the question. Is it going to be a black jaw crusher, or is it going to be a hammer mill, or is it going to be a ball mill, or is it going to be a fluid energy mill? Anyone? Sorry. So ball mill requires a grinding medium. So that I told, right? Requires grinding medium. That I explained it before itself. What about in case of black jaw crusher and hammer mill? So both of them also requires a grinding medium. This one also and this one also. Whereas fluid energy mill is something that is not actually going to require an energy medium, because there the fluid itself will basically do the breaking, or you can say that do the size reduction process. So that is basically the type of mills which do not require a grinding medium. So fluid energy mill is the answer. So any questions related to these three of what we discussed right now? Anyone? Any questions? Yes, no. In case if you have questions, feel free to ask. Okay, I think I can move forward. So question 4, 5 and 6. Large value of Rittinger's numbers indicate that a material cannot be crushed. Less energy is required to crush the material. More energy is required to crush the material. And the D, none of the above. Large value of Rittinger's number. So that Kr value that we discussed, this particular value, sorry, this particular value is going to be very large. So what does that typically mean? Yes, anyone? Think from the formula. So it's going to be that lesser energy is required to crush the material because larger the value of heating is constant, which means that very less, if you're going to supply less energy, the particles are going to be broken to the desired size. Now, roller crush. No, before that, let's move to question 6. So how is this energy is wasted in communication process? Is it going to be in the form of heat, sound, or both heat and sound, or none of the above? Where is actually that energy is getting wasted in the communication process? Heat, sound, or both heat and sound? It's going to be both heat and sound, right? Yes, correct. Because this we saw in case of both heat as well as the sound of the rotating equipment, that energy is actually going to be wasted. Now come to question 5. Roller crusher works on shear, compression, both compression and shear, and the none of the above. This is going to be simpler. Roller crusher, think from that perspective. Roller crusher. Is anyone? Roller crusher. So think from that perspective and let me know the answer. I'll wait for some time. So it's going to be both compression and shear, right? Because it's going to roll. So you're going to charge it with some grinding medium. This is something that we saw in case of ball mill also. So because of the action of the grinding medium and as well as the rotation, the balls are actually going to be, the material is going to be subjected to both compression and shear force. Any questions? Or shall we move forward to the next question? Any doubts? Any confusion? Anything that you would like to discuss? Okay, then I think we can move towards the next one. Okay. Rotation does not occur in which of the following mills? Ball mill, hammer mill, fluid energy mill, and none of the above. Obviously, one option can be neglected because you now know that ball mill rotation happens, so this can be neglected. Now, between hammer mill and energy mill, which of the following rotation does not occur? Be careful, rotation should not happen. Hmm. Sorry, that was a slide that the same slide got was duplicated twice, so that was very good. Any guesses between hammer mill, fluid? It's not none of the above, so I'm going to remove that option as well. So between hammer mill and fluid energy mill. And it's going to be fluid energy mill, right? Because fluid is going to cause the particles to break. It's not going to be any sort of rotation or any other force. So fluid energy mill is the answer. Question 8, you need to tell me the answer, no options. So the question is state the limitations of Kick's law. Straightforward question. What is the limitation of Kick's law? Yes. Mm. Yes. So only answer is it does not depend also does not depend on size of the particles. It's going to be irrespective of the particle size. So that is the limitations of the Higgs law. Now, I hope no doubts in this. This is a straightforward one. Somebody rightly said just it does not depend upon the size of the particle. Obviously, you can also put another limitation is that the mechanical losses are not being considered, but this one is something that is primarily for Higgs law. So does not depend on size of the particles. So shall we move towards the next one? So for cement, which of the law is most suitable to find out the energy consumption? Is it Kick's law, Rittinger's law, Bond's law, or both Kick's and Rittinger's law? Cement. So remember, cement is the material, and based on this, you need to judge which law will be suitable to calculate the amount of energy consumed for the size reduction process. Is it going to be Kick's law, Rittinger's law, or Bond's law? Or both Kick's and Rittinger's law? Any questions? Any so far, or what is the answer for the question number 9? Remember, cement is the word. If you can identify whether this cement is going to be coarse or fine, you can get to know the answer for this question. Any guesses for this one? Just a second before you. Okay. So it's going to be Bond's law, because cement is going to be something of a material which is going to be the intermediate size. So that is the reason Bond's law is going to be the most suitable law to find out the energy consumption. So any questions in the first 9? Any doubts in the first 9 questions? Anyone? Any questions? If no questions, then shall we move forward? Okay. So let's solve this problem before coming to the question number 10. So I'll read out the question. In a crushing operation, feed size is reduced from 50 into 10 to the power minus 4, that is 5 mm to 1 mm. The total power that is consumed by the crusher is 80 kilowatt, out of which 10 kilowatt is consumed when running empty. If the feed mass flow rate is 10 tons per hour, calculate the following: Rittinger's constant, Kick's constant, and Bond's constant. So you are going to do a crushing operation. Feed size is going to actually reduce from 5 mm to 1 mm. Total power is actually given as 80 kilowatts, and out of which 10 is going to be consumed when running empty. Feed mass flow rate is given as 10 tons per hour. You are supposed to calculate the 3 bonds constant. So how to solve this problem? One thing here, you can take power and energy alternatively. Any guesses on how to solve the problem? Anyone? So, as I said, you can take this power consumed and then the energy to be like, what is it, alternatively. So, let's first solve rating of Kick's constant, then you can try solving for Rittinger's and Bond's constant. I'll take out the expression from here. So, E is going to be 80 minus 10, because we are not going to, because see, it is written 10 kilowatt is consumed when running empty. So when you are going to run something empty, whatever the amount of energy that gets consumed is something that is going to actually get counted as a mechanical loss in the form of heat or sound. So you are not basically counting for that. So that particular amount of energy is going to be lost as a, is going to be actually lost in the form of heat or sound. So that is the reason I'm going to subtract, because in Kick's law we do not take this energy into consideration. So 80 minus 10, that is 70 kilowatts. M, you know, that is 10 tons per hour. And dF, just let me take it from here. dF is going to be 5 mm and dP is going to be 1 mm. So if you are going to calculate based on this, you can easily calculate your Kk. That is Kick's constant. So it is 70, just a second. It should be like this. It is 70 times 1000 divided by 10 tons per hour. You are supposed to calculate this tons per hour in terms of You can either keep it in tons and then calculate the kicks constant, or you can convert it into meter and then calculate the kicks constant. It's your wish. So let us put this. I'm going to calculate it in terms of kgs and watt per kg hour, so that would be easy for me. This is going to be, so df by dp is going to be 5, right? Ln 5. So if you do the calculation, it's going to be 7, because 1000 can cancel, and 70 by 10 is 7. Is going to be kk kicks constant times, sorry, kicks constant times ln pi. So that would be nothing but kicks constant is equal to 7 by ln 5. So let me use the calculator. 7 7 divided by ln, what is ln 5 of 1.609. 609 unit is watt per kg. That's all. So kicks constant value is 1.609 watt per kg per hour, or you can write watt hour per kg. So this is how you calculate the kicks constant. Now based on this, you are supposed to calculate the Rittinger's constant and Bond's constant. So try calculating one. Let me give you some time so that then I'll start solving. You can start with the Bond's constant, then we can go to Rittinger's constant. So start with Bond's constant first. Yes, any answers from anyone? I think you just need to substitute different kinds of expression and then the plug in the values, and then I think you should be able to get. So will you be able to calculate this on your own? I think for the Rittinger's constant, I need to give the value of dvs for both the particles as well as the feed, so that I'll give it. But apart from that, will there be any confusion? Yes, no. So will you be able to take it as a kind of a tasks? Okay, so this will be the task to solve for both Rittinger's and Kick's constant. Sorry, Bond's constant. I'll give out the value of dvsp and dvsf. Now let's move to this one. Question 10. How to calculate the critical speed of revolution? And how do you calculate the critical rotational speed? Which is the correct formula? Yes, anyone? Critical speed of revolution. It's going to be option C. I think I won't be able to highlight this. Let me know one. And then uh, just a second. So it's going to be 1 by 2 pi divided times root over g by r. So based on this, you are supposed to calculate the answer for the second one. Hence, calculate the critical rotational speed of a mill of 1.2 meter dia charged with 70 mm diameter balls. So you just need to substitute R value in terms of meters and then you'll be able to solve the problem. So what would be the answer? Yes. Anyone? It's going to be just, I mean, like value is going to be n. I'm going to keep it as n. You can keep it as nc as well. 1 by 2 pi. So 2 times 3.14. This entire expression times root over g by r. So I'm going to take g as 9.8 or you can take it as 10 by 70 diameter. That is going to be 0.07 meters. Is it correct? Hmm. This expression whole power zero point 0.5. That's also 9.8 by zero point 0.7, 140, and 140 per zero point 0.5 is going to be 11.83. So n is going to be 11.83 by 6.28, which will be nothing but 1.88 revolutions per second. Because omega value is 2 pi n, we need to calculate n is nothing but omega by 2 pi, value of omega is root over g by r, so this is going to be revolutions per second. That's all. So this is how you will calculate the critical rotational speed in terms of revolution per second if a ball is going to be charged with so much amount of diameter of balls. So I hope you will be able to solve question 11. In case if you have any doubts related to question 10, please let me know. We will take up with question 11 in the next live interaction session. So kindly solve it over the week. Any questions? Anyone? This is for today's session. So if you have any doubts, please let me know. Or if you want to discuss anything, you're welcome to do so now before we conclude the session for today. Okay, so I think let me stop share presenting. So if you have no doubts, I think I can conclude the session for today. So thank you all for joining today's live interaction session. I hope you find this live interaction session useful. Our next live interaction session, that is the last live interaction session for this course, will be on 15th of August from same 5 p.m. to 7 p.m. So I hope you are able to access the course content as well as the video lectures for the live interaction session that are uploaded. In case if not, please access the content. So in case if you're not able to find it, go to the course content page. On the left hand side at the bottom, you can see problem solving session. Once you click on that link, you will be directed to an Excel sheet where you can find the YouTube recordings of this video as well as the presentation folder. You can access it from there. My email ID will be mentioned there. So you can, if you have any doubts, you are welcome to email me. I will try to answer to that questions as soon as possible. Or in case if not, you can also drop your questions in the Q&A section. So I take this as an opportunity to thank Professor Shabina Khanam ma'am as well as the NPTEL team for providing me this opportunity to interact with you all on this Saturday afternoon. So let's meet for our last live interaction session next week. Till then, thank you and have a great week. Have a great weekend and work through your course over the week. And let's see next Saturday. Thank you and bye.